Okay, so my name's Nicholas Crouch. I'm going to do a revision seminar for Applications of Quantitative Methods in Finance. So with not a lot of questions coming through for me to talk about, what I'm going to do is I'm going to pick on some of the topics that I haven't seen an awful lot of through the previous revision seminars that are mentioned in the notes. So first thing to say, I work for the Math Learning Centre, which is centrally funded by the Deputy Vice Chancellor Academic and Student Experience. And that means I'm not part of the maths department. So what the advice I'm going to give you is about the mathematics. It is my best understanding of the mathematics involved, but it is not the same as what you would get from the School of Maths. It's important that if you have any queries about what you're doing here, you can talk to the people at the lecturer for this course. I'm not actually sure who that is this time, but you can talk to the lecturer and get the actual information for the questions. All right. So the mathematics involved, definitely know what I'm doing, but there may be some nuance to the way the question is asked. There are some things that, some of the things that I may go a little beyond what the course did, or I may not cover a key point that the lecturer would have liked to hear you say. This is where you refer to your notes or you check with the lecturer. You look at the things like your assignments for guidance about what the right thing to do is. Okay, so the first thing that I thought I'd talk about is Lagrange multipliers. So Lagrange multipliers is a way of finding an maximum or minimum value over a constrained region. So we've got ourselves a multivariable function with a multivariable constraint, and we're going to try and find the maximum value. So I like to tend to think of this is if you've got a road through the hill, right? The hills being your multivariable function, and the road is like the constraint. And so we don't want to find, so we might know the maximum for the function, but we actually want to know the maximum along that road, right? Because that road is the points we can get to. So this is a way of thinking about how to do this. Okay, so what I'm going to do is I'm actually going to have some old sample exams, very old sample exams, we should point out. And so what I'm going to do is I'm going to try and find a question from them that actually uses Lagrange multipliers for the solution. And that way we can talk directly about that particular thing. It, of course, may not have come up. So you can ask a second while I have a bit of a scan. You here for the AQMF one? Application of Quantitative Methods in Finance? Yes?
I have received this email for mathematics.
Yeah. Which one are you? What topic? Oh, yeah, AQMF. Yes. Oh. Yep. Sweet.
Oh,
if you have questions, just ask me. Okay. So what we will do is we will look at this screen. No, we need to focus. Okay, so we'll see down the bottom here from this sample exam from years past. Down the bottom, use the method of Lagrange multipliers to find the maximum value of the utility function subject to the budget constraint. Okay. Feel like if I do this, and so maybe the best way for me to organize this. Okay, that's not much. Okay, so we've got our question here. And so your f of x or f of xy is equal to x squared, y squared, and your constraint. So x plus 2y is equal to 20. First thing we've got to do is we've got to form the Lagrangian, and that means we're going to rewrite this equation as a equal to 0 equation. And so my Lagrange equation is going to be my objective function, the thing I'm trying to find the maximum of. So that's just x squared, y squared. And then just debating whether I should check that. I usually go plus lambda by 2x plus 2y minus 20. We've got to be a little bit careful about this sign, and I do. Give me half a second while I check. So if we look what I've got here, which ones? Calculus notes. So there's a bit of a thing about whether I use a minus or a plus here. This how we do. So it actually won't make any difference to the final answer, but it will make a difference. So, but I would like to make sure I try and stick to the way your lecturer has done this. So what I'm going to do is I'm going to go and that one. That one. I'm actually going to quickly search through the notes. And so one of the things we should be doing when you're actually revising at home, actually going through and finding these things here. So we look at page 28. So what we'll do, okay. Yeah, so I'm just swap this around so that I can do this so you can see what I'm looking at here. Yes, do that. So for those of you playing at home, the thing I forgot to do today is plug in the screen so that you can actually see so that people you can see. And let's think for a second. I'm going to have to do sweets. Thank you. Do that. I forget. There are sometimes I forget when I'm doing stuff because I'm focused on the thing I'm trying to say. Which reminds me, what we should do is we should go here and we should go. So what I'm going to do is I'm going to put that over there. So you can see here that when we're forming the Lagrange equation, right, we've got our g of x, y equal to 0. So we've arranged that in the correct way. So when we've done this, we've arranged our function in the correct way. And we've just formed the Lagrange equation by doing our objective plus lambda times the constraint. All right, so let's go back to what I was doing and go. So this is the right way to do this. So that's why so I'm going to refer to the notes occasionally just to make sure I'm doing the right thing, because while there are some slight differences, if we do this in the correct way, then we can actually, there's an interpretation for this value of lambda if we were to find them. All right. So the idea is what we're going to do is we're going to try and work out, we're going to find what they call the first order conditions. All right. So we're going to find the partial of the Lagrange with respect to x, the partial of the Lagrangian with respect to y, and we're also going to do the partial of the Lagrangian with respect to lambda. All right. So when we're doing this with respect to x, we differentiate the x. So x squared goes to 2x. We're treating the y as a constant because it's a partial derivative. So we're timesing by y squared as well. And then when we come down here, we're differentiating this. And so my x gives me 1, so it's lambda times 1. So I'm going to have lambda. And we're going to set that condition to be equal to 0. So in a similar way, when we do the y, we're going to get 2x squared y plus, this time it's going to be 2 lambda is equal to 0. And when we get down to the next step, so we've gone through all of this, we are down to, when we differentiate with respect to lambda, this is constant, this is effectively constant, but we're actually getting x plus 2y minus 20 is equal to 0. You'll notice that this bit here, all right, this bit here is just the constraint that we started with, all right? So what we're going to do though, all right, is we're going to use these two to get, and the relationship with lambda, so that we can get an expression. All right, so if I call this equation 1, and I go, 1 is going to give me, so my 2x y squared plus lambda is equal to 0. I'm going to rearrange that to tell me that 2x y squared is equal to minus lambda. And similarly, if I do 2, I'm going to do this 2x squared y plus 2 lambda is equal to 0. So I'm going to do the same thing, put the lambda on the other side, 2x squared y is equal to minus 2 lambda. I'm actually going to divide through by 2 as well. X squared y is equal to minus lambda. Now I've got this situation where I've got minus lambda here and minus lambda here. And so that means I can actually make those two parts. I can actually go, this thing here is equal to this thing here. So 2xy squared is equal to x squared y. Now, what this is going to do, all right, I can cancel out one of these x's here, and I can cancel one of my y's here. And so I'm going to have 2y is equal to x. This is awesome. So what we've done is we've used these first two equations. Am I off the page? I'm off the bottom of the page. Sure. And so I've used my first two equations up here to generate this relationship between x and y. And I'm then going to put this relationship in here. All right. Now, notice how conveniently the constraint has a 2y, and I've got a 2y. So what I'm going to do is I'm going to go my x plus 2y. I'm going to say equal to 20. I'm going to put the 20 over the other side. And then 2y is equal to x. So this is x plus x is equal to 20. And so x is equal to 10. And if x is equal to 10, all right, so 10 is equal to 2y, therefore y is equal to 5. Now, one of the things, if we go back to the question, so my optimal point would be 10 and 5. If we go back to the question, all right, see if we go back here, use Lagrange multipliers to find the maximum value subject to this constraint. So we actually haven't got sort of anything that tell us whether we've created a maximum or a minimum. Okay. So what we can do though is we can sort of go in this region because of the form of the function, because if we look at the partial derivative of just f of x, so partial of f of x, that's going to be 2xy squared. If I look at this point, where did we go? So if we look at this, look at our point down here, take that function value, that function value. All right, this is going to be like 2 times 10 times 5 squared, 25, 50, 500. This is a positive value. So that says as x increases, y, the function value is going to increase. And similarly, if you do the f with respect to y, you can get 2x squared y when evaluated by f with respect to y at the point 10 and 5. We are going to get, let's see, what's this going to be? So 2 times 100 times 5. So 200 times 5 is 1,000. So this is saying we're increasing in the y direction. If I just, I've kind of run out of room here, but if I just draw that constraint actually comes down to x is equal to 20, y is equal to 10. So that constraint comes through here. All right. And so we're actually, because this is a utility function, we're only actually interested in sort of the positive root. So we're not interested in any of this stuff out here. So we're only interested in this point here. And our point 10, 10, 5, 10 would be about here, 5 would be about here. And so it's about halfway along the line. That's where our maximum value is going to occur. This is not required for the question. So the graph is just for me to illustrate what we're seeing, okay? But it helps you see where we're going with this sort of problem, okay? So because this constraint is a line through here, this function looks like a quadratic in the x direction and a quadratic in the y direction. And so we've got this sort of nice sort of curve, upward shaping curve, but the maximum point comes quite early on, okay? So that would be just pause momentarily and go, does anyone got any questions? You okay? Yeah, cool. All right. So I haven't, because I don't get to see the exams anymore, I can't be sure. Have you had enough time to sort of take notes yet? Oh, pause. At this point in time, I should go, all of the seminars go up online. What I'll do is I'll just pause my internet. Where is it? There we go. All right. So this is the Mass Learning Center website. All right. And so I've actually gone to the Application of Quantitative Methods resource page. All right. And so there's a bit of stuff about our various revision seminars. So you'll notice that from last year, David did a seminar on critical points, curves from differential equations, integration by parts. A few years before that, we've got implicit differentiation, differential equation. And then we've got some on probability, Markov chains, miscellaneous topics. I wonder what that is. So you can see we've actually got seminars going back quite a long way. And part of what I've done here is I've actually looked over this and gone, we haven't talked, the reason I chose the Lagrange multipliers is it's not something that has occurred for a while. And I'm only trying to guess at what might be in the exam so that I can talk to you about things that are possibly going to be there or not. Now, okay, so did you actually have anything you particularly wanted to discuss? That's okay. One of the next things I thought about, looking at what has been done and what hasn't been done, is so looking at the things that have been done and haven't been done. I sort of thought I might try and find a question. So I was looking over this and I didn't see anything that talked about producer and consumer surplus. All right. So cheers. I'm just actually having a bit. So if you look, what I'll do is I'll put this here so you guys can see what I'm doing. So just having a bit of look at, so there's a question on Markov chains, there's binomial distribution, there's a question about normal distribution down here. That was page 5, just look at page 4. So we've got a question about doing Venn diagrams, got something about discrete probability. So this is like a conditional probability question. I might actually talk about doing that because I think that's on my list of things we haven't talked about recently. So I'll talk about, maybe we'll talk about doing conditional probability for a minute. Okay, so let's read this question a little bit more carefully. Make sure I've got the right idea. So drug is tested. A drug test is 92% effective in detecting the use of a particular performance-enhancing drug in athletes. The probability that the test gives a positive result when athletes is not using the drug is just 5%. Assume that 10% of athletes are using this use this particular drug. Draw the theory diagram. So the first thing we're going to do is we're going to try and lift the information out of that question. All right. So because this information about how effective the test is for testing positive, all right, is dependent on whether the athlete's assuming it, so using it. So what we're going to do is we're going to, that first step, point 1 is uses the drug. And so the other one, 0.9. And so we're saying 10% of my athletes use this drug, 90% don't. So then when we come down to test positive, so it's going to look a little bit funny, but I'm going to go test positive complement. All right. So we're saying those 9% of effective if detecting a performance enhancing drug. And so I can go, that means this number. So this actually represents the probability, this number, the 92% is a conditional probability. So probability of testing positive given using the drug is equal to 0.92. And so this is a 0.92. And so this one, because these two probabilities have got a sum to 1, 0.8. 0.08. Watch me for that. Okay, this is where I go. Unfortunately, I occasionally do this thing where I write the wrong number. Okay, so this next piece of information that says 5%, that is the probability of testing positive given that we are not using the drug. And so that's sort of this probability here. And so we've got test positive complement. And so this is 0.95. Okay. So, so the question actually says, what's this? Where did I steal this from? Oh, this is the okay. So so this is a way, this is actually the answer. Draw the figure diagram that represents this probability. And so these are the probabilities that I've used to work out, and I've written them in appropriate notation so that we can do this. We can work out what it is. Okay, now, if an athlete tests positive, what is the probability he or she is actually using the drug? Okay, that's kind of an interesting thing, because what we've got, we want to know the probability. So this is part B, probability that using the drug given tested positive. Okay, now this is where we have funky rule. So the funky rule says probability of A given B is equal to probability of B given A times by the probability of A divided by probability of B. All right. Okay. So I'm going to put this next to me here. So we have got, so in this case, the A would be using the drug. We have the probability of using the drug. Sweet. That's one of the things we have up the top here. So we actually have probability of using the drug is equal to 0.1. And so probability of not using the drug is 0.9. So let's write out what the thing is. Probability of using given test positive should be equal to probability of testing positive given using times by. So this is probability of using on probability of testing positive. Okay, so if we think about the things we have here, all right, this one we have from up here, this one we have from over here, this one we don't have, okay? And so that means we've got to calculate that value. And there's a rule that says, so if we look at this, we're going to go probability of testing positive is equal to probability of testing positive intersection with using plus probability of testing positive intersection with not using. Because everyone's either using or not using, whoops, there we go. I can do this, I can actually work this out. And so if I go up to my tree diagram, I'm going to do this one because it's still on the screen. My probability of testing positive here, all right, and not using. So I multiply those two probabilities. The probability of testing positive and not using is going to be 0.9 times by 0.05. Okay. Now, so that number should be 0.045. I reckon. Feel free to check my maths because when I'm doing this, I forgot to bring a calculator to do my calculations for me. And so I've got this thing. So if I go the same thing up here, probability of testing positive, given that we're using and using, is equal to 0.1 times by 0.92, which would be equal to 0.092 conveniently, making my life nice and easy. And so when I add those two numbers up, 0.9092 plus 0.045 down here. And so that should be equal to, so it should be a 7, and 1 and a 3. All right. So let's put these numbers in here. All right, so my probability of using given tested positive is going to be equal to probability of testing positive. So 0.92 times by 0.1 on, I've already worked this number out, 0.137. Wrong number. Where, yeah. Since I don't know, I'm not going to try and calculate it by hand. What I am going to do is I'm going to put it into Excel to do the calculation for me. All right. So all right, what we'll do is I'll show you what I'm doing with Excel here. So if I want to work this out, what I would do, so if I'm doing here, to get it to do a calculation, I do put an equal sign, 0.092 divided by 0.137. This number is 0.67. I'm going to say 0.67. I'll do that. Two significant figures. Now, so if I test positive, there's a 2/3 chance that I was using. All right. So let's go back to that one. Let's look at the next part of the question. Okay. Oh, okay. So this is going to do the same thing, but we're going to flip it around. Okay. So we're going to turn around the information and go, if the athlete is test negative, what is the probability that he or she is using the drug? Oh, not. That's an interesting question. I'm kind of curious about how this is going to work out. So what I'm going to do, this is going to look a little bit strange, but anyway, I want my diagram there. I wonder if I can put, yes, I can do this. All right. So we can almost see the diagram there. Ooh. All right. With the people in the chat while we're doing this, people in the Zoom meeting, if you're not actually in the chat, what you can do is just post questions in the chat so I can answer them. And hopefully I'll notice if you have a question. So we're trying to go, so in the same way, we want to know probability using not, so we want to know probability of not using, given they haven't tested positive. All right, so it's good to not try and get you to stick with condition, complement of condition for this sort of thing. All right, and in the same way as before, that means we're going to do probability of not testing positive, given they're not using, times by the probability of not using on probability of not testing negative. Okay, so hopefully we've got some of these numbers already worked out. So probability of, so this I'm going to have to get from the diagram. So it says we're under the branch that says not using, and we're going to go testing negative. So this number is 0.95. Probability of not using 0.9. That's from the diagram. Probability of testing negative. All right. So this is that same probability of test positive complement. So we're going to have to go through that same process of working out what this is going to be. And so probability of the complement of testing positive is going to be probability of complement of testing positive intersection using plus probability of testing positive complement intersection the complement of using. So we're going to times, so on our tree diagram, that is, we're going to sort of times down here. So we're going to follow the path, both paths that get me to that number. And so let's see, so using it would be 0.1 times by 0.08 plus 0.9 times by 0.95. All right, that should get me my values. And so this is 0.008 plus, anyone want to have a guess? I'm going to just get Excel to do that calculation for me so that I don't get it wrong. .8, 0.855. And so this number is equal to 0.863. All right. So we've got all my numbers to put in. Let's actually just take it up here and go 0.95 times by 0.9 on 0.863. This number is actually this number here. So when we come down to, so probability of wrong. Feel free to tell me I'm not showing the right screen. I should be able to do that one. There we go. Okay, so what I'm saying here is this value here, this value here is actually what we just worked out here. So we've actually got this number. So we're going up to the thing we're talking about. Probability of not using the drug given that I didn't test positive is equal to 0.855 on 0.863. Quick drag to the Excel. And so what I'm actually going to do is I'm going to go equal to, this is this number divided by this number. Ooh. So this is saying that if I test negative, extremely likely that I'm not using. But if I test positive, I might actually, there's still a 1/3, 1 in 3 probability or approximately that I'm not using the drug as well. So suppose that hey, what happens here? Okay, so so the last part of this question, is suppose the assumption that 10% of the athletes were using the drug is not correct, and that actually 20%. Okay, so that means what we're going to do is we're going to repeat that calculation with 20%. And so I reckon what's going to happen with this. So if we go back to what we did here, all right, we're going to change these. We're going to change our, whoops, can't see it. We're going to change this probability to 0.2. And so, so my probability of using is going to be equal to 0.2, and my probability of not using is going to be equal to 0.8. And so when I come to finding out all these other probabilities up here, so because I use that value in here, so my probability of testing positive intersection using is now going to be equal to 0.2 times by 0.92, which is going to be, who knows? It should be equal to 0.184. So my probability of testing positive complement is going to be 0.8 times by 0.8 times by 0.05, which is going to be 0.04. And so when we what we did to work out what my probability of testing positive is, that was going to be summing these two numbers up. All right, so it should be 0.184 plus 0.04, which should be 0.224. Let's pretend I've got that right. And so when we use that value in here, so we're trying to sort of follow what we did before, and we've got all these numbers worked out. And so this value here is the new denominator. So my probability of using, given I tested positive, is going to be equal to, so this number is my denominator, 0.224, and this value is actually my numerator, 0.184. All right, and that is, don't know, can't tell you just yet. So I'm going to equal 0.184 divided by 0.224. Ooh, 82%. I'm going to call it just 82. 82%. So you can see we've gone up considerably just by increasing the probability. So it's just one of these things where we're using that conditional probability to work out what possible values you could have. Okay, that would be trying to do conditional probabilities. And so you can see all I'm using, so this rule that we're focusing on doing, I'll go back to this version of it. This is part of Bayes' rule, all right? And there's this second part. This part here. This is the total probability thing. So what we're saying is if I have two sets, a set U and its complement, that are mutually exclusive, all right? The key part about that is they're mutually exclusive. Then to work out the probability of a set, we can break it into the intersection of set with other set plus, the intersection. So T complement in union the U, and the T plus intersection union complement, and that's both parts of it. And we could extend it. So the Bayes law, I'm actually just going to put that in down the bottom here. The total probability thing is if I want the probability of some set A, we can write that as probability of A intersection BI is equal to 1 to n. So we're literally going probability of A intersection B1 plus probability of that on the screen. No, it's not, because I'm in it. Sure. Probability A intersection B2 plus plus probability of A intersection Bn. So provided these Bn cover all the possibilities and they're mutually exclusive. So we have that Bi intersection Bj is equal to the empty set. I is not equal to j. And they cover all possibilities. So we do union I is equal to 1 to n of Bi is equal to the universal set. Okay. Do we have any questions at this point in time? We'll give that just a second. All right, cool. So, all right. Let's see what else I've got in this exam that might be a good question to talk about. Okay, so we're going to go back a little bit. I might pause momentarily just to talk about this first question. So, use the definition of derivative to find f dash of x. Notice this first question is worth 4 marks, all right? So what we're going to do is I might just, right, this is one of those things where a lot of students actually lose a couple of marks just by not following the process correctly, all right? So this thing is going, so my f of x is going to be x squared plus 3. And so f dash of x, the definition says is equal to like limit x h goes to 0 of f of x plus h minus f of x on h. All right. So we've got this. This is actually what the definition is. Where students lose mark is this requires composition of functions. And so we want to be a bit careful about showing that particular thing. All right. So when we say x plus h, we're putting x plus h where there's x. And so that would be x plus h all squared. So notice how I had to put brackets around it. Minus, and I'm going to put brackets around f of x as well, because I've got a minus sign out the front. So I'm being very careful with exactly how I'm putting this. So in theory, this is just algebra from this point on. This is actually the key step. So if you think about it, I needed to do this and I needed to do this. The next couple of steps of algebra, you need to show what you've done. But if I expand this out, I'm going to get x squared plus 2xh plus h squared there's going to be a plus 3. Expanding the minus through this, it's going to get me minus x squared minus 3, all divided by h. So I can observe we've got an x squared here and a minus x squared here. I've got a plus 3 here and a minus 3 here. So let's write that with those things removed. So I've got 2xh plus h squared. I've only got those two things. And so to make it clear what's going to happen, h goes to 0. I'm going to go h by 2x plus h. So I'm factorizing that h out of that numerator. And so now I've got a h in the numerator and a h in the denominator. Now, I can actually now evaluate this limit because I'm not dividing by h, which is going to 0 anymore. I can just let h go to 0. And so this is going to be 2x. So if you look at what's actually involved in this, right, this question said 4 marks. All right, they're allowing you a fair bit of time, but they want you to state the definition and they want you to get the composition of functions right. This line is the key part about this. There's a little bit of, so if you think about it, there's like 1 mark for this, 1 mark for this, 1 mark for this bit here, all right, and then 1 mark for this. There is those 4 marks. This is actually not a difficult question, but it's important that you sort of remember to put in the steps of the working so that you can actually have the correct answer. There's no point with a question like this, they're going, hey, we're going to actually start this exam by giving you something that you should be able to do reasonably easily, and letting you go through that thing. All right. Again, just for the people here, if you have a question, feel free to sort of just say something. Or if you're online, have a thing in the chat. So if there pokes up a question that it looks like I've forgotten, please just interrupt me. Okay, so I'm going to thumb through. We're going to go back to looking at this, and so you notice actually this other version of the exam I've got says almost exactly the same thing. The first thing they did is do a differentiation from, they call it from first principles in some places, but from the definition. So using the definition from first principles, those are the sort of, some refer to the limit definition of the derivative. They're all ways of talking about it. Notice how the other function we looked at was like x squared plus 3. This, we're keeping it to simple functions, all right? But, and again, it's worth 4 marks. It's worth 4% of the exam. So it's actually a considerable portion of the exam marks. Okay. Revenue. So there's like rate of change questions, derivative questions, find all the critical points, use the second derivative, maximum value of this. I'm just trying to look for something. Most of that we've done in past revision seminars. So there's questions about using trapezoidal rule. I didn't notice anything about using trapezoidal rule. That may be an option. This is sort of more conditional probability. Again, conditional probability. That's your life chain. Binomial random variables, that might be worth talking about. Normal distribution to variable calculus. Okay. So I was specifically looking for something that might have talked about doing what you call I'm talking about producer and consumer surplus. So, but I don't think we do that at all. So just, this is one of those things where when I've looked at the exam, I've gone, oh, should we talk about, well, I've got these terribly out of order now. All right, want to grab, so I did actually want to sort of, I would like to not have to make a question up, if I can talk with this, because I thought that sort of thing would be useful, but just please give me a moment while I try and find a useful question to sort of talk about. There we go. That's what I'm talking about. So, see with this question here, for a particular commodity, supply and demand functions are given by supply and demand. What is the equilibrium price and quantity? Calculate the consumer surplus and the producer surplus. So what I'll do is I might actually work through this question. Yeah, this is actually from assignment only a couple of weeks ago. All right. Again, I'm not part of the School of Maths. I don't know about what's going to be in the exam. I've looked at the course material in the last couple of days to have an idea what I'm doing, what sort of things you've done. But this is just having a look at what we've talked about before and what we might find useful. There's lots of revision seminars you can upload, and this revision seminar will go online as well. All right. So I might go for a clean page. And go. All right. So we'll put there is a solution already there. Okay. So some of this is just, when I say just algebra, I don't mean it should be easy. I just mean, and for the exam, so this is actually quite likely the sort of level of complexity, because this is not the most complex problem that you could have for this type of question. Okay, so when we're finding the equilibrium price and quantity, we literally just make supply equal demand. That's what the equilibrium price and quantity means. We should have seen that in Intro to Financial Maths. All right. So first thing I'm going to do is multiply both sides by the denominator. So we love fractions, but the first thing we do with fractions is we get rid of them. All right. So usually that means multiplying by the denominator. So I'm going to have 10q by q plus 4. Again, this is a sum, so I'm putting brackets around it so I don't make a mistake, like I don't forget to expand out. And so I'm going to have 10q squared plus 40q is equal to 600. Ooh, it's a quadratic. So 10q squared plus 40q minus 600 is equal to 0. One of the things I'm noticing that's going to make my life a little bit easier, and you're allowed to do, right, is go, hey, every one of these coefficients is a multiple of 10. So I'm going to put the 10 out the front. And so I'm going to have q squared plus 4q minus 60. Okay. Now, there is two things to do, all right? One of which, so in my head, right, it's almost second nature now because I've been teaching maths for so long, is when I see a quadratic, I look at this number and go, what two numbers multiply together to give me that number? And I want their sum or difference to be 4. Now, because one of these numbers is negative, that means it's a difference. I want one to be positive, one to be negative. All right, so I'm going to put my 10 here. The easiest one is 6 and 10, right? Yeah, so I'm going to go q plus 10 and q minus 6 is equal to 0. And I can check q squared plus 10q minus 6q, that's going to get me 4q. 10 times minus 6 minus 60, ooh, it's going to be right. Yeah, so this is going to get me q is equal to minus 10 or 6. It's a quantity, people. So the beautiful thing about financial maths is we go, it's a quantity, it must be a positive number. Okay, so I can find this thing here. What I'm going to do at this point in time is I'm going to do a rough sketch. And I say rough sketch because rough is about the way it goes. I haven't got nice graph paper, so it's hard to actually do. So I'm going to put my quantity along here, and I'm going to put my price along here. And so when I look at my supply curve, 10Q. So that means that's my supply curve. All right. And when I look at my demand curve, so my demand curve here is going to have, when I put in Q, so that's going to be, if I put in Q is equal to 0, I'm going to get 600 divided by 4, which should be 150. And so you notice I kind of drew in the asymptote, even though it's not going to go through that point. All right. So because my quantity is never negative, but just to get the feel for what the function looks like by observing that this function has vertical asymptote when Q is equal to -4, I can sort of know what that feeling looks like. I'm only interested in sort of that bit, but that can help me draw the picture. Okay. Now, so we've just worked out that this quantity is 6. All right. If I then put that back in here, so if I go, if my quantity is 6, my supply, and because that's going to be 60. So I'm actually marking in the values that I'm interested in. Okay. Now, all right. The question actually goes on to say, calculate the consumer surplus and calculate the producer surplus. All right. So I'm going to go consumer surplus. So consumer surplus actually works out to be this part of the graph. Yeah, that's the right way around. I'm pretty sure that one is my so here, this bit. All right. If I was to do that, I've got to calculate that as an integral. So that's going to be the integral from 0 to Q star. And so it's my it's my demand curve minus consumer surplus, we should put that in, minus my my equilibrium price. Okay. So let's just go through and do this. So this thing should be let's put in the numbers. So 0, so this was 6. This is my demand function. So 600 on Q plus 4 minus 6 dq. Okay. So I'm going to integrate those two bits separately, but I'm going to do it sort of all in the one thing. It's kind of a bit of a test. Realistically, what I should do, actually, we'll do it like 0, 6, 600 on Q plus 4 dq minus integral 0, 6 of 6 dq. And this one here, what I really should do is I should actually go, all right, so integral from 600 on Q plus 4, I should go U is equal to Q plus 4, and so du is equal, du on dq is equal to just 1. So I can actually write this as integral of 600 on U du, and so that allows me to go, that's like 600 ln of U, which would be 600 ln of Q plus 4. All right. strictly speaking, I should do it that way. In actual fact, this is one of those situations where, because it's a simple function, all right, I don't actually need to go through that process of doing the substitution, but this is like literally what's happening, all right? And doing that, actually writing it out could actually help you work out what the correct answer is. And so I'm going to jump back to the actual integral. So this is going to be 600 ln of q plus 4 minus, I'm just going to go 6q because we should be okay with that. And so we are going to get 600 ln of 6 plus 4 is going to be 10 minus 6 times 6 minus, and then we're going to have brackets. We're going to put in the 0. If I put in this, it's like 600 ln of 4 minus 0. So 600 ln of 10 minus 36 minus 600 ln of 4. I'm going to do a dodgy trick. I'm going to combine those two things. So it's going to be like 600 ln. Because it's ln of something minus ln of something else, I can do 10 on 4. All right, sweet. Make sure I've written that in. Now, so what I'm going to do is I'm going to go equals 600 times each XL, so I've got to remember to put that. And so I've got 10 divided by 4, so I can put that into the thing. And then I'm going to go minus 36. And we have ourselves a number. Our number 513, so equal to 513.77 dot dot. Okay. So, whoops. So we can do the same thing, all right? So while I've got my diagram here, we'll grab a different color and we'll go, so this bit here is actually my producer surplus. Okay, so producer surplus. Now, so what we're actually doing with the producer and consumer surplus is we're doing an integral to find that area where we do integral of upper function minus lower function. Okay, so that's how I came up with this. That's how I remembered the formula. I drew my little picture. All right, and I'm going, oh, okay, let's see what that works out to be. So we're going to put my little picture there. So I've got it right there. And so when we come down to doing producer surplus, that's going to be the integral from 0 to q star of, and so this is where we go p star minus the supply curve. So we just put in the values, 6, this was 60, blah, 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 blah. Oh, yeah, no, it was 60. So, we paying attention? We'll come back to that. We will go, ooh, yes, this is what I mean. My apologies for those people watching home. I forgot to put in my P star. I put in Q instead of P star. And so this number is actually out. Why don't we go straight back to Excel and just go, if I go this number here, see if I go here, all right, all I can do is I can just go that, and it should be, that feels a lot better. This number should be, ooh, I ran out of things. I'm going to put it over here. Consumer surplus is equal to 189.77 dot dot dot. Okay, sure. Sounds like a thing. Okay, let's go back to the thing. Well, hey, got my picture, got my thing going. Okay, so this one, and then minus 10 Q. All right. there are little things. I got a positive value here, and it should be a positive value if I've done it right. If you get a negative value, quite often what that means is you've got the order of the functions around the wrong way. So first thing would be to check which way they should have been. If you've done that in the exam though, right, if I put these numbers around, then what you do is you go, hey, I put those numbers in the wrong order. I should turn them around so that I can work out what that is. I should just do the integral. Integral of 60 with respect to q is going to be 60q. Integral of minus 10q is minus 10q squared, 2. So this is q to the power 1. I add 1 to the power, divide by the new power. Technically, there's like a q here, which was q to the power 0. I added 1 to the power to make it q, divided by the new power, which is 1. So I did the same thing. Whenever I have just a constant, there's implicitly a variable to the power 0 next to it. So it makes it nice and easy. So this is going to be 60 times by 6 minus 10 times 6 squared on 2 minus, and then it's going to be 60 times by 0 minus 10 times by 0 squared on 2. These numbers, they're all zeros. 360 minus, so if I do 10 times 6 squared times divided by 2, you know what we should do? We should go equal to 10 times by 6 to the power 2 divided by 2. I feel like that's the right number, 180. And so this is equal to 180. Whoops. Ooh, 180. So, and if I go back to my diagram, we're saying that bit is equal to 180. One of the things I'm going to point out at this point in time is those bits look about the same size. Yeah. And so that kind of feels like we've done the right thing, right? We've got the right sort of answer for what's going on here. All right. And it's important to sort of take a moment and go, does what I've said make sense? That same thing, like if I get a negative value for one of these things, I've made a mistake. And all I do is I say, hey, I made a mistake. That would have been I put these around the wrong way. I can fix that by just changing the sign. All right. You do want to check that where if you did that, you didn't accidentally calculate the producer surplus rather than consumer surplus or vice versa. But you want to be, if you've made a simple mistake like that, then you want to just, so you can just say, hey, I made a mistake. These numbers should be, this is what they think. There is value if you're doing an exam to focusing on to going, hey, this was a mistake. All right. I have made a mistake in doing this particular question. And so I will talk about doing rectifying that. All right. Cool. Do we have any questions to this point? I'm gonna keep asking because there might be something that crops up. The last thing I had on my list to talk about, so like I said, I went through the stuff. I've had a bit of a look at what we've got online and to sort of have a bit of an idea of what might be causing problems. And so trying to sort of make sure that in the absence of questions, I've got a plan. I have a plan, really I do. So what I was going to do, I'm going to talk about my list. There's discrete probability distribution. And so what we're going to do here. So discrete probability. I've seen a question here about probability. These exams are a bit old. All right. So not there. There. This would be a discrete probability question. All right. I kind of like doing this from this perspective. So let's go and talk about this question. Okay, so 2 dice are thrown and the sum of the 2 dice is recorded. The table below gives the number of ways the various sums. And what is the probability of throwing a sum? Okay, so maybe I don't want. Let's see if I've got a better option. Pause momentarily. No. I'll come back to that one in a second. Okay. Because this is, I want to sort of find out something like this where we've actually talked about, we've actually got these, you get to see these things happen. So what is the probability of throwing a 6? So this first question, it's like worth 1 mark. And really all you have to do is look up the table. Okay. So it's important. So this is some of those things where sometimes you look at questions and go, I don't know what to do. It's really important to take a moment and go, actually, that first part of the question I can probably do. All right. Even if you had no idea what to do with the rest of it, that first part of that question, you go, oh, I can just work it. I can just work this thing out. Right. Nice and simple. All right. So if I do question 2 part A, would be probability of x equals 6. All right. Probability of the sum is equal to 6. So literally I look at the sum here and go, that is going to be, so there are 5 ways it can do that. Technically, I've got to do over the sum of all the number of things, all right? So because we're treating each one of these things as equally likely, each of these outcomes, I should add up all of these numbers. So it should be like 1 plus 2 plus 3 plus 4 plus 2 plus 1. So if we go that 3, 6, 10, 15, 21, 26, 30, 33, 35, 36 is equal to 5 on 36. We kind of knew that anyway, but my point was you could actually just add up this number of ways. All right. So 5 of them give me the result out of all of those possible number of ways. So I might have had different types of dice. For example, I may have put in like a 7-sided dice. I don't think there is such a thing as a 7-sided dice, but I'm going to ignore that detail. And so to work out what we're treating each outcome as equally likely, we've got 5 out of the total. All right. So find the probability of throwing a sum that is odd. All right. So probability x odd. And so what I'm going to do is I'm going to go sum of dice. And so for every odd number, so 3 is, there is 2 possibilities, plus 4, plus 6, plus 4, plus 2 on, I've already added them all up, so I'm going to say 36. And so this is going to get me, so that number is 10 and that number is 8. So this is like 18. 2 plus 4 is 6, plus 6 is 12, plus 4 is 16, yeah, 18. 18 on 36 is equal to a half. So we can simplify, right? With these fractions, it's important to sort of do that next step. If I see sort of, 18 on 36, you may not recognize that immediately as a half, but you should sort of go, oh, well, they're both even numbers, I'll divide them both by 2. And I'll end up with 9 on 18. And then you might go, that feels a bit ominous, that. So you can always simplify your fractions. Notice there's not a lot of working involved with this, right? But I have written down exactly what I've done. And it's really kind of important you get into the habit of writing stuff down in the exam, right? I've marked exams like this, all right? And I've had a situation where, as an example, what might happen, the person has written 1 on 3, and they've just written 1 on 3. And you're kind of going, I don't know what's happened, right? But say you have a penchant for writing 3s instead of 2s. If you've written this, and then you've written 1 on 3, I go, oh, I can give you full marks for that, right? It's really important that you give me something I can give you marks for, okay? So that's why we're doing this. Find the probability the sum is 4 given the sum is even. Okay, so probability C. So we want probability even, probability x equals 4 given even. All right. So that is like probability of x equals 4 and even divided by the probability of even. Now, I'm going to do a little bit of a trick. Probability of even is equal to 1 minus probability of odd. I can get away with doing that because even and odd, my number is either even or odd. So I can just go and I can do this. And since I've already calculated, I can go 1 minus a half, which is equal to a half. We should have one. The probability of being even and 4. So 4 is contained, the event that the sum is 4 is contained within the event that the thing is even. All right. And so I can actually just go, well, it's the same as the probability of being 4. And so my probability of x equals 4 given even is equal to probability of x equals 4. Boop. Yep. And so this should be 4. 4 was like 3 on 36 divided by a half. I've got fractions in fractions, so I should make sure I put brackets around the actual fractions. All right. And so I'm going to have 3 on 36 times by, when I'm dividing by a fraction, I turn it upside down. And so I'm going to have 6 on 36, which is going to be 1 in 6. All right. There is one more part to this question. What is the expected value of the sum? Okay. So to work out the expected value, so part D, expected value of x is equal to sum of xi times probability x equals xi. That's actually what your formula in your notes says. Okay, so what that means for us, for our particular thing, is we are going to do, I'm going to write it out. It's kind of going to be a bit tedious, but there is a rule, my rule of thumb, that says if it's a summation, all right, and there's less than about 10 to 12 numbers, sometimes the easiest thing to do is write it out and add them up. It also says that if there's more than 6, there's possibly a 6 or more, there's possibly a trick. There is a trick, I'm not even going to bother with it because it's just so much easier to just go, hey, we've got all these numbers written out, let's just write them out. And so this is going to be, so it's going to be probably, so x is equal to 2 times the probability of 2 is 1 on 36. Plus x is equal to 3 times the probability of 3, which is 2 on 36. Plus 4 times by 3 on 36. Plus 5 times 4 on 36 plus 6 times by 5 on 36 plus 7 times by 6 on 36 plus 8 times by 5 on 36 plus 9 times by 4 on 36 plus 10 times by 3 on 36 plus 11 times 2 on 36 plus 12 times by 1 on 36. And so we've got all that there. Let's push the page up. That denominator is going to be 36. And so this is going to get me 2 plus 6 plus 12 plus 20 plus 30 plus 42 plus 40 plus 36 plus 30 plus 22 plus 12. Well, okay. I have my feelings about this, but let's do it. So this is going to be 8, 10, so that's 20, 40, 70, 112, 152, 188, 188. So this would be 218, 218, 240, 240, 252. All right, at this point in time, we have seen me do this by hand. And so I'm going to go hashtag, I make mistakes all the time. But under the heading of, I don't know what this should be, so I'm going to divide through by 2. So that's going to be like 126 on 18. Now they're both still even. So I'm going to do, so that denominator is 9, so this is going to be 63. Those are both divisible by 3. And so that should be 21 on 3. That should be 7 on, hang on, nope. So that should be 3, hang on, nope, 7. Try that again. 7 and 7. No, it's 7. Woohoo. All right, beautiful. I'm going to point out at this point in time, if we take this thing here and go in, so these denominators are the same. This is symmetric. And the middle number is, the middle sum is 7. All right. And so that agrees with what we expect. Literally, the expected value is what we expect. Okay. And so I would say, okay, that gives me confidence that we've done this the right way. Okay. So there are little things that tell me about what I expect to be the right answer. Okay. Cool. What I saw. So now, is there any area that you would sort of think I should try and talk about? What's that? Okay. I'm actually going to just so I've got these past exams. I don't think we do this anymore, but I'm going to show you this. All right. This is actually what they concluded with the exam for calculating normal values. All right. Now, you notice how if you've looked at your normal charts, have you seen normal charts before? For a normal distribution? Yeah. So one of the things that happens with some of these courses, this is not the most common form of normal chart, all right? All right. And it's important to recognize that, because what they would quite often do is they'll do something which is slightly not the usual thing for the chart they'll give you, all right? So this thing is given, we know the thing is symmetric. This has only given me the positive half. And so for any negative value, I'd have to use the fact that the normal distribution is symmetric. And it's important to go, oh, okay, I've actually gone and done my normal thing with using exploiting some of the symmetry of the situation. So it's important that we sort of go, okay, we could be doing this sort of thing. I actually wanted, yes, so I actually wanted to talk about, I sort of thought while I do this, because I've got myself about 20 minutes left to do another problem, talk about something else. And so I thought maybe what I'll do is I'll talk about doing a binomial thing. Let's see, that was page, I'm trying to keep track of what I'm doing here. And so let's have a read of this question. Okay. So an investment is modeled by a binomial random variable. The probability that the investment increases by value in value by $50 in 1 month is 0.65. It decreases by value by $50 in 1 month with probability this. Let X denote the number of increases in the investment over 12 months. Okay. So our X, so we've actually defined our random variable as the number of increases. Okay. So, and so X equal number of increases. That did not work out very well. That looks a lot better. Okay, so what we should be doing is we should be going, for it to be binomial, so n would be equal to 12, and p is my probability of success, which we've said is 0.65. Okay. Yeah. There is sort of two ways of doing this, right? So we've just done that thing. So binomial distributions are discrete random variables. And so my expected value of X could be given by Xi probability of X equal Xi. All right. But because this is a binomial random variable, I actually know that it's going to be equal to n times p, which is equal to, so 12 times by 0.65. All right. So this is one of the things where the point I'm trying to make is that my formula is quite horrible, but there's actually a special case. So if I know my nodes well enough, I've got a shortcut for how to solve this problem. I have no idea what 12 times 0.65 is off the top of my head. So I'm going to go equals 12 times by 0.65. 7.8. 7.8. All right. So this means that I expect to have 7.8 increases over that time period. Okay. Sound like a thing. I feel like that's a thing. All right. And if I'd worked out the probability, we should actually possibly pause for just a second though. All right. So I've sort of stated this thing says, so it's modeled by a binomial random variable. So whenever we're talking about something like a binomial random variable, there are things that we assume. All right. So for it to be a binomial random variable, my events must be independent. So we're actually saying the probability I went up in this month is independent of the probability it went up in any other month. All right. So that's one thing, that the probability that I go up in any given month is the same across all of my months. And there's a fixed number of trials. So in this case, by saying it's a year, we're saying we've got 12 periods when we're possibly increasing. And by saying it's binomial random variable, we're actually saying that that probability of increasing is the same for every one of those months and that they're independent. So if we're going, hey, if we're trying to decide what distribution we've got, fixed number of trials, independent events, and fixed probability of success, those are the things we look for a discrete random variable. And so we are going to go, this is going to go off, man. All right. So calculate the standard deviation. So sigma of x. All right. Do you happen to remember what the formula for sigma of x is off the top of your head? I reckon I'm going to ask you to check this for me because I think it's n times p times 1 minus p. But I just want to check it to make sure. Yep, good. And so we're going to go square root of 12 times by 0.65 times by 0.35. So, whoops, I got. All right. So we've got our formula, we've got our thing. So again, I'm not even going to try and work that out. So the first thing I'm going to do is I'm going to go 12 times by 0.65 times by 0.35. That's the bit under the square root. And so I'm going to go equal square root of that number. (1.65) other numbers. All right. When we do, so we've got this actual value. We notice it's not 1.65, it's 1.65 and other digits. All right. So I've only written down 3 decimal places or 3 significant figures for this number, just to be clear. Okay. Now, the reason I thought this question was good, all right, is this next part. The random variable y models the change in the value of the investment over the 12 months. Give an expression for y in terms of x. And so what we said, so because this is a thing that's telling me how many increases I get, and an increase is an increase by $50. All right. So my y should be equal to 50 times by x. But if it didn't increase, it decreased. There was only 2 options, going up and going down. There is none of this staying steady. And so I've actually got to take away 50 times by, so my number of trials minus x. So I should write this as 50 times by x minus 50 times by 12 minus x. I got that right, did I? Ever look at that and go, okay, so this is going to be 50x minus 50 times 12 is going to be 600. And then minus 50 times minus x is going to get me plus another 50x. So this is actually 100x minus 600. Okay, so this kind of like, so at the moment we're sort of saying, we said that we expect 7.8 rises. All right. So that means we should expect sort of 4.2 decreases. And so the difference in those two is only like about, so 4.2, 7. Is about 2.5. 2.5. I'm going to ignore the details there. It's 2.6. And so my total increase should be about 2.6 times that increase. All right. And so this kind of okay, this for me was just a little bit, this was just a little bit surprising when I worked it out. Okay. I was a little bit going, oh, is that right? But it kind of, when I talk about it, I go, oh, okay, there's going to be more rises than there are decreases. I should end up with a positive value. That should be right. And so use your answers from C to find the expected value. So there's a thing that says, if I have the expected value of AX plus B, it's going to be A times the expected value of X plus B. So my expected value of Y should be equal to expected value of, and so we've worked it out here. So 100 x minus 600. My formula says, so my A comes out the front, that's 100 times the expected value of x minus 600. Okay. Woohoo. Still on the screen? No, I'm not. But I've got my expected value of x right up here. So this is going to be 100 times by 7.8 minus 600, which is 780 minus 600, which is 180. This kind of feels right. Okay, this feels in that ballpark for what I expect to see. All right. And we're going to ignore the fact when I was talking about what I expected to be, should have been 3.6 rises, not 2.6 rises. Anyway, little detail. So I can follow this process through. One of the other things that we could do we remember that, actually I won't say that. Scratch that. I don't think I saw that in the notes, so I'm not going to try and talk about it. So yeah, I think we're kind of at a natural point to stop. Is there anything else you'd like to look at? What's that? It's okay. I think what I might do is actually we've gone through the things that I wanted to go through. So to reiterate some of the key points, firstly, these revision seminars by the Maths Learning Centre, we are not part of the School of Maths. We know the maths, we don't necessarily know what your lecturer is looking for. These past exams are not an accurate indication of what might be in the actual exam. They are what has been in the exam in previous years, okay? So, and these are quite old, these ones, all right? But the material in theory is still the same. So, but the emphasis of the course may have changed over that time. There are more revision seminars available online. So all of these revision seminars are available online. And so the other thing is the Maths Learning Centre is available for you. So I've seen you in Maths Learning Centre before, I'm sure. And so Maths Learning Centre Level 3 East Hub Central. You can come and talk to us about your maths, about any of these maths courses that you're doing. And so Maths Learning Centre is available for you to talk about any course with maths in it. All right. So you are possibly doing a finance degree if you're doing this course. And so there are other courses you might be doing, like intermediate econometrics next year. You can come and talk to us about that as well. All right. So those things are available for you. I think I'm going to say good luck with the exam. I'm going to stop sharing my screen. All right. If you have any more questions, feel free to join us. Don't forget, for those people who are online, the Maths Learning Centre has an online forum. And so you can join us online as well. All right. Thanks so much. Thanks so much for coming along. Made this thing a little bit easier for me. I hope you got something out of it. No. Makes it, like I said, makes it a lot easier for me if there's someone in the room. But yeah. Yes, you can.